Well, hello everyone. Today we will be talking about the derivative as rates of change. Now, to kind of put a little bit of context into this, imagine that you were driving your car and you were driving merrily boggling along, and suddenly you got news that there was some emergency somewhere that you had to be at. So you're driving, you start speeding up, and you might start driving faster and faster and faster until you get to your destination. Maybe it was a hot date, maybe it was a member of the family that was sick, whatever it was. You started driving faster and faster. So you sped up a little bit, and then your position as time went by looked like this. So notice you start slower and your speed is increasing. Your position function is looking like a curve that's going upwards. So the motion of objects can be modeled pretty well by what we're doing here. To each of these, we can apply some mathematical graph per se. And we're going to do a couple of examples. So we have many things in context right here. We have our position function. We have our velocity as the derivative of the position function. And if our position function was s of t, then our velocity v of t will be equal to s prime of t. Acceleration a of t is equal to the derivative of velocity as equal to v prime t, and it's also the second derivative of the position function, which is s double prime t. Now, speed is a magnitude of velocity, so it's the absolute value of v of t. Now, just to differentiate, velocity is a vector function. That means it has both magnitude and direction. So you're going like 60 miles an hour east or west. That is velocity. Speed is just talking about just the 60 miles an hour that you're going. Also, acceleration is a vector quantity, right? So it has size and it has direction as well. If velocity is negative, that means we're moving to the left or we're moving down. So think about the coordinate graph. If you move in the left, then you're going in a negative direction. Or if you're moving down, you're doing a negative direction. Otherwise, you're going positive. So if you're moving right or you're moving up, that's positive. Okay, if an object is at rest, then it's zero velocity. And if you think of velocity of a position function, that would be where your slope would have a zero slope. Thinking of curves, it would be a maximum or a minimum, or if you're thinking of a line, it would just be a horizontal line. So let's look at a couple of examples. The position of a particle along a coordinate axis at time t is given by s of t is equal to t cubed minus 4t plus 2. Find v of 1 and a of 1, and then use these values to answer the following. A, is a particle moving from left to right or from right to left at time t equals 1? B, is a particle speeding up or slowing down at time t equals 1. So let's look at what something like this would look like. So here is our function, or the position function. S of t is equal to t cubed minus 4t plus 2. Now recall that our velocity function is the derivative of our position function. So v of t is equal to s prime of t. And if we take the derivative of t cubed, that would become 3t squared. Derivative of minus 4t, that's just minus 4. The derivative of a constant is 0. So our v of t function would be 3t squared minus 4. Our acceleration function is the derivative of our velocity function, that is v prime of t. If we take the derivative of 3t squared, we end up with 6t. Let's look at v of 1. V of 1 is equal to 3 times 1 squared minus 4, that's equal to negative 1. And let us also look at the a of 1. A of 1 is equal to 6 times 1 equals 6. Now, are we moving from left to right, or are we moving from right to left? Notice that we are moving from left to right. Why? Because we said that if our velocity function was negative, right, then we're moving to the left. So whenever velocity function is negative, we are moving to the left. Think about like going on the horizontal axis, going to the left is negative. The next part is what is happening. What is happening? Are we speeding up? Are we slowing down? So let's look at the velocity at 1 and the acceleration at 1. The velocity at 1 was -1, which means that the v of 1 was less than 0, and the acceleration was 6, which means that the a of 1 was greater than 0. So v and a are going in opposite direction. Think of vectors going in opposite direction. The net effect of that will be that your velocity will be decreasing because the positive acceleration is outweighing or going against the negative velocity. So our speed or absolute velocity is decreasing, so the particle is slowing down. So that is how I would treat a problem like that. Next thing, let's talk about estimation and change. Now, remember, we're given or a function on an interval defined on a closed interval, a plus h, and the amount of change will be like the change in the y values or change in y, that is f of a plus h minus f of a. Recall that our average rate of change formula was f of a plus h minus f of a over h, and our instantaneous rate of change was limited as h approaches 0, f of a plus h minus f of a over h. Now, let's do an approximation for small values of h. So when h is really small, then the f prime of a is approximately f of a plus h minus f of a over h. So that's the derivative, right? The derivative at a is equal to that. So f of a plus h, then, if we rearrange this formula, f of a plus h would be equal to f of a plus f prime of a plus h. Now, graphically, what that will look like is if we're on this blue curve f, and we took the tangent line at a of f of a, we're using that tangent line to estimate the y value of what it would be at a plus h on the curve. So the estimate or error is the difference between this point, a plus h, comma, f of a plus f prime of a times h. That's the difference. So what we're saying is that we can use this orange dot to estimate this blue dot that is right above a plus h. Right? We're saying if it is really small, then they're not too far from each other. So that's what we do with estimation and change. So what we're going to do then, we're going to apply this to some problems, regular graphing problems, then to population problems. So if our question is if f prime of 3 is equal to 2, no, f of 3 is equal to 2 rather, and f prime of 3 is equal to 5, you want to estimate f prime of 3.2. That is just going from 3 to 3.2. What would be that function value, knowing the value at f of 3, and we know the change, what is happening, what is the rate of change at 3, what is the tangent line at 3. So let's look at that and see how that plays out. So our question is, if f of 3 is equal to 2 and f prime of 3 is equal to 5, estimate f prime of 3.2. Estimate f prime of 3.2. So let's do that right now. So remember, our f of a plus h was equal to f of a plus f prime of a times h based on our estimation. So we're using the f prime of a plus f of a plus f prime of a times h to estimate our f of a plus h. right? So we know our h is equal to 3.2 minus 3, which is 0.2. So let's plug in a for 3, which is our x value, plus h. That's going to be equal to f of 3 plus f prime of 3 times h, but we know h is 0.2, so we can plug that in. And so we're going to have f of 3, which is 2, plus f prime of 3, which is 5, that times 0.2. So overall, we get equal to 3. So our estimate for the function value at 3.2 would be equal to 3. So not knowing exactly what the function actually is, but we know that we're using the function value at 3, and it's the change in the rate of change of 3. We can use this formula, and if we plug in all the relevant parts, we have f of 3.2 is approximately 3. Okay, so let us apply that to some real life problems. Let's think about population problems. So the number of members in a population at a time t is denoted p of t, and then the growth rate of the population is its derivative p prime of t. So what we will do, we'll use p of t and p prime of t to estimate a future value, let's say p of t plus something else. So here's our question. The population of a city is tripling every 5 years. If its current population is 10,000, what will be its approximate population 2 years from now? So we know it triples every 5 years. You know, the population triples every 5 years. Every 5 years, right? Every 5 years. You know, the current population is 10,000, and I want to know its approximate population 2 years from now. So let's do it. You know, let's call this time p of 0. Let's call in 5 years when it will triple, p of 5. So p of 0 is 10,000, p of 5 is 30,000. So the p prime of 0 would be approximately p of 5 minus p of 0 over 5 minus 0. That would be 30,000 minus 10,000. That should be 10,000 over 5. So that's going to be 20,000 over 5. That's going to be 4,000. Now we want to find p of 2 years from now. So that would be like 0 plus 2, where 0 is our current year, and then 2. So that's p of 2 is going to be approximated by p of 0 plus p prime of 0 times our h. There will be 2. So that's going to be equal to 10,000 plus 2 times 4,000. So we end up with 18,000. So in 2 years from now, the population will be about 18,000. So this is like using our f of a plus h is equal to f of a plus f prime of a times h. Okay, so f prime of a times h. Let's use this. All right, times h times h. Right. So that's the same ideas. Okay. In addition to using our work for change and estimation for population, we can also use it for revenue, profit, and cost functions or approximations. So in this case, we're using the marginal costs or marginal revenue and our marginal profit situations. We know that cost was C of x, marginal cost is MC of x, that's C prime of x, and so on. We're using the same ideas. However, in the questions that we're doing now, we will take our h to always be 1. So let us apply that to our problem. The price of X barbecue dinners is 9 minus 0.03x, and the revenue is x times p of x, and that will be negative 0.03x squared plus 9 of x. And now we're going to quickly just run through an example. Really, we want to find out if we have 100 dinners, what's the cost of the 101st dinner? And so just applying that through, we just use a marginal revenue function to approximate the 101st inning and we get an answer 3. We'll talk a little bit more about this in the future, but for right now, thanks for watching and see you next lesson.